Traditional robots move by sliding or rolling, generating friction across their entire body length. Growing robots, however, extend their length by continuously turning their body inside out, a process known as eversion. This mechanism ensures that the robot tip experiences zero relative motion against the environment, eliminating sliding friction at the point of contact. The extension force is generated internally, typically by pressurizing the folded material reservoir. The robot effectively pushes its own skin forward. This continuous material inversion allows the robot to navigate complex, constrained environments without accumulating drag along its body, fundamentally changing how locomotion is defined in soft robotics. The speed of growth is directly proportional to the volumetric flow rate of the internal fluid, or the rate of material feed. Eversion relies on maintaining a significant pressure differential between the internal cavity and the ambient environment. The robot structure consists of a flexible tube stored in a reservoir, folded back upon itself. When pressurized, this internal fluid forces the material at the fold line, the eversion front, to invert and extend. The energy required for extension must overcome the material's bending stiffness and the friction between the inner and outer layers of the tube at the fold. Minimizing this internal friction is critical for efficient growth. If the internal pressure exceeds the critical buckling pressure of the material, the robot extends smoothly. Otherwise, the tube may collapse or wrinkle, halting forward motion. The selection of materials is paramount, requiring polymers that exhibit high flexibility, low elastic modulus, and exceptional fatigue resistance under repeated folding and unfolding cycles. Common choices include thin-walled polyethylene, nylon fabrics, or specialized elastomers. These materials must withstand significant hoop stress during pressurization and high localized strain at the eversion front. The thickness of the material directly influences the required actuation pressure. Thinner walls require less force, but offer lower resistance to puncture. Furthermore, the material must possess a low coefficient of friction on both its internal and external surfaces to minimize energy loss during the inversion process and interaction with the environment.
Eversion actuation primarily utilizes fluid power, categorized into pneumatic and hydraulic systems. Pneumatic systems, using compressed air, offer rapid extension speeds but typically generate lower forces, making them suitable for lightweight exploration tasks. Hydraulic systems, employing incompressible fluids like water or oil, provide significantly higher force output and better stiffness control, crucial for applications requiring load-bearing or manipulation. The fluid delivery system must precisely regulate flow rate and pressure to maintain stable growth velocity. A key design challenge is managing the volume change in the reservoir as the material is deployed, often requiring a compensating mechanism or a continuous feed spool. While the tip experiences zero relative motion, friction still occurs between the robot's deployed body and the surrounding environment, especially in tight turns or rough terrain. To mitigate this, some designs incorporate external lubrication, often using a thin layer of fluid released at the eversion front. More fundamentally, the eversion process itself minimizes drag accumulation. Since the robot is always extending new material, the deployed surface area that has already contacted the environment remains stationary relative to that environment. This contrasts sharply with traditional snake robots, where the entire body length slides, accumulating substantial drag forces proportional to the contact length. Steering a growing robot requires actively controlling the direction of the eversion front. This is typically achieved through differential actuation or embedded tendon systems. In differential pressure steering, the robot tube is segmented, and pressure is selectively increased on one side of the tip, causing the material to preferentially buckle and extend in the opposite direction. Alternatively, internal tendons running along the length of the tube can be tensioned. Pulling a tendon on one side induces curvature at the eversion front, guiding the growth path. Precise control of the steering mechanism is essential because the robot's trajectory is determined incrementally, and errors compound rapidly over long extension distances. A major limitation of soft-growing robots is their inherent lack of stiffness, making them susceptible to external loads and gravitational deflection. To overcome this, researchers employ post-extension stiffening mechanisms. One common technique is granular jamming, where the internal cavity is filled with particulate matter and a vacuum is applied, locking the particles together and rigidifying the structure. Another approach involves using phase change materials, which are fluid during eversion but solidify upon cooling or chemical activation after deployment. This allows the robot to transition from a highly flexible state during growth to a rigid, load-bearing structure for manipulation tasks. The ability to navigate highly constrained and tortuous paths makes eversion robots ideal for applications where traditional rigid manipulators fail. In minimally invasive surgery, these robots can navigate delicate anatomical structures, minimizing tissue damage by growing around obstacles rather than pushing through them. For infrastructure inspection, they can traverse complex pipe networks, ventilation shafts, or collapsed rubble, deploying sensors or communication lines. Their inherent safety, derived from their soft structure and low impact force, is critical in human-robot interaction scenarios and sensitive environments like nuclear facilities or biological laboratories. Current research focuses on overcoming limitations related to deployment speed and energy density. The need to carry the entire material reservoir limits the robot's operational range and payload capacity. Future designs are exploring segmented growth, where material is fed from external sources or synthesized in situ. Integrating sensing capabilities directly into the eversion material, such as stretchable electronics, will enable real-time environmental feedback and damage detection. Developing multi-material eversion systems that can selectively deploy stiffening elements or adhesive surfaces represents the next frontier in creating highly adaptable, autonomous growing robotic systems.